justice, Mekayamen. Welcome, everyone. Today is a bizarre Monday, or rather an unbreakable one. So today I'm going to do something special. Some of you might be aware or not aware of a mathematics YouTuber, German mathematics YouTuber by the name of Flammable Maths, or known as the cult followers, and which I call him as well, Papa Flammy, Jens Fehlau. And he has done a very extraordinary Jojo meme post best on a so-called complex fraction diamond. So essentially he got a fraction and he created a tower of them, layering fractions on each other. And the mad lad figured out a way to actually go and create an explicit formula that generates what the summation, what the ratio of this entire monstrosity is. He did this one at first for any general fraction tower. I'm going to call it fraction diamond, although it's an emerald here. Fraction diamond with one entities in them. He later on went and generalized this for the Gaussian integers. So basically the set of all consecutive integers from 1 plus n being added together for the integers. And today I figured I would do a different take on it. Since he did it with the very nice integers, I figured why not go and do it with logarithms. So yes, I'm upping the stakes, upping the ante, so to speak. And a key thing that we need to know when we're looking at division here is that be aware that it is not commutative. Specifically, that if you have one fraction being divided by another fraction, then you have to take this denominator fraction, flip it around, in other words, take the reciprocal, and then multiply it by the fraction in the numerator. He does this, he likes to call this thing over here where we split up the two fractions, the so-called main vinculum. I don't think I'm pronouncing it correctly. And there are three main steps as to how he managed to do this process for his original thing, and which I will do for like this natural logarithm diamond emerald as well. First, we have to go and define a numerator sequence and a denominator sequence. I define it here as y sub n and z sub n, and the ratio as x sub n, as he does before. Those are the same variables he used. Step 2, we're going to look at some basic pattern-like examples, so very analysis-based thinking. And then we're going to, from that, see a pattern and derive a recurrence relation. So if you remember what a recurrence relation is, it's simply a sequence that is defined in terms of its previous terms. So it has to go and start somewhere. And usually when you go and prove that recurrence relations exist, you typically do so through induction or other sorts of algebraic tricks. So one famous recurrent relation would be the Fibonacci sequence, which I also covered in this channel. Feel free to take a look if you're interested. But then also, this recurrence relation only gives an implicit description of this mathematical object here. If possible, we would like to go and derive an explicit formula, and we will do that. And in between step 1 and 2, I'll also be introducing you some preliminary necessary pre-calculus algebra things, because in order to do this, we're going to need to revisit our natural logarithm and factorial laws. Yes, those will pop up a lot, along with some more exotic concepts that Papa Flammy has covered in his videos. Please go and take a look at those videos here. I've attached them either now in the video or they'll be put into the description. And before I get onto it, just please feel free. I don't really care about likes or subscriptions, but at least please feel free to comment. I'd love to hear any sort of dialogue into this little pet project of maps that we might have discovered on our own. So I hope you enjoyed the show. Okay, first, the necessary computational algebra prelims. We're gonna have to use two things, logarithms and factorials. First one is the law of addition for logarithms in general. If you're given any real integer, a, b, then the natural logarithm of their product equals the sum of their logarithms. In other words, ln of ab equals ln of a plus ln of b. Now pretend that we keep doing this. Look at this particular layer of the complex emerald fraction. We have natural logarithm of 2 being added up to natural log n, a finite string of length n of logarithm of so-called real numbers. And were to do natural logarithm of 2 plus natural logarithm of 3 plus so forth and so forth up to natural logarithm of n minus 1, and then finally to natural logarithm of n. We should be able to go and use this, go backwards from this addition property over here to this product here. So we can condense all these numbers, 2, 3, n minus 1, and n, into a single logarithm of 2 times 3 times dot, 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 stuff missing in between, times n minus 1 times n. And note, remember that the definition of any positive consecutive integers being multiplied consecutively next to each other is in fact the factorial. That's just the definition. That's just a factorial by definition. Of course, this is assuming that you are obeying the well ordering principle, which is a very subtle principle that is often overlooked. So well ordering principle. Which claims that the integers have a least element. So then this simply becomes natural logarithm of n factorial. Okay, eventually, it's not going to be obvious, and this is why it's very important that we need to look at examples for this particular kind of problem. Not every problem works this way, but for this particular problem, examples are very important because the actual recurrence relation we're going to derive for the numerator and the denominator is actually not going to contain natural logarithm of n factorial, even though it appears that it should because we have these two bars over here. It in fact is going to be, the recurrence relation in the numerator is going to be y sub n equals y sub n minus 1 divided by natural logarithm of n plus 1 factorial. And in the denominator, it's going to be z sub n equals natural logarithm of n plus 1 factorial divided by z sub n minus 1. Check, double check my work once we go through the examples, just in case there's an error, because you can make mistakes with indices a lot. I do, and sometimes I freaking hate induction proofs sometimes because of changes in indices. Okay, now I will go over the examples to show why we end up with n plus 1 factorial instead of just n factorial. Okay, hello. So I have the numerator and denominator recurrence sequences of relations shown here. And now I'm going to show like why it's the case that you have n plus 1 in the index. So if we write this out, first we'll know that for our most simplest case of this power fraction tower, we're going to end up with something along of x1 of natural logarithm of 2 in the denominator and natural logarithm of 2 at the bottom, which is just simply equal to 1. So x1 equals 1 and y1 will equal natural logarithm of 2. Z1, I'm sorry, will equal natural logarithm of 2. That's just a seed in this case, or an initial value. Now, we're going to take a look at it again. We're going to look at x2, the next case. That's going to be this second layer of the top and the bottom here for y sub 2 and z sub 2 respectively. Z sub 2, I should honestly do in terms of y2 first. So y2 equals natural logarithm of 2 over natural logarithm of 2 plus natural logarithm of 3. Z sub 2, on the other hand, is going to be the flip reciprocal of that. So natural logarithm of 2 plus natural logarithm of 3 over natural logarithm of 2. And as a question, just in case, obviously why we're not starting with natural logarithm of 1, that's because natural logarithm of 1 just simply equals 0, which is the same thing as e raised to n to the 0th power equals 1. So that doesn't work in this way, in this case. And that's why we resort with natural logarithm of 2. Otherwise, we'd have 0 over 0, and that's simply an indeterminate form, which we can't work with. Okay, keep doing this pattern onward. We'll get, so yeah, this will give us x2 equals, as I mentioned before, this will simply be natural logarithm of 3 factorial. So this will be ln of 2 over ln of 3 factorial divided by ln of 3 factorial divided by ln of 2. And here now we have to use the property of complex fraction division, or dividing two fractions. We need to flip this around. So we end up getting that natural logarithm 2, or natural logarithm of 3 factorial divided by natural logarithm of 3 factorial divided by natural logarithm of 2 equals simply times itself, which in this case will simply give us this quantity being squared. And note, now note carefully, please. This is x of 2, but yet we still end up with a 3 over here. That is 2 plus 1. So for the index value like 2, you end up with natural logarithm of 3 factorial over here. I'll do it again for a different layer. This time for seed x of 3. Of course, I'm going to need like y sub 3 and z sub 3 now. Okay, so part of y sub 3 equals simply ln of 2 over next layer. Ln of 2 plus ln of 3. Next layer, ln of 2 plus ln of 3 plus ln of 4. And then if we do z free, which is the denominator term free, we'll just flip this around the main vinculum. So we get ln of 2 plus ln of 3 plus ln of 4 divided by ln of 2 plus ln of 3 all over ln of 2. Now remember, like our fraction rules and the stuff I mentioned about factorials, then we should get over here ln of 2 over ln of 3 factorial, ln of 4 factorial. And then here we would get ln of 4 factorial in the top, and then everything else at the bottom. Ln of 3 factorial, ln of 2. And now, if we were to go and find this in terms of the ratio element at n equals 3, x of 3, well, then we would simply get x of 3 equals basically this over that. So ln of 2 over ln of 3 factorial, ln of 4 factorial, ln of 4 factorial over ln 3 factorial, ln of 2. And then you flip and like multiply this over, so you end up getting ln of 2, ln 3 factorial, ln 4 factorial. Okay, let me make sure I'm thinking about this like correctly. I get the ln 2, flip it up to the top here, ln of 2, then ln of 3 factorial, and then divide by ln of 4 factorial. The ln of 3 factorials cancel. So I'm getting ln of 2 over ln of 4 factorial squared. And now I think I might have made an error somewhere, but if so, this will unfortunately ruin like for the even terms, which I'll talk about for the sequence I generate for this video. So I technically have this be equal to 1 over ln of 4 factorial. It's going to take me a long time to go and take a look at these. So you as a viewer, please tell me if I made a mistake somewhere in the layer result, either over here or in the layer continuity of the video. But basically, yeah, this is x of 3. And if we were to do this with the general numerator and denominator sequence I gave you here, which is simply that, well, x of n equals y sub n over z of n, and we define like y of n as the previous term in the numerator divided by natural logarithm n plus 1 factorial, and then divide this by natural logarithm of n plus 1 factorial divided by z of n minus 1. Just flip this around and I get yn minus 1. So the numerator times the denominator over natural logarithm of n plus 1 factorial, this thing squared. Now I'm going to do a quick derivation to get rid of the y's and z's and express this recurrence relation purely in terms of ratio terms, xn. Why do I do this? This will help us tremendously simplify calculations, as you'll see in a minute. Z sub n minus 1. Let us go and make a substitution here. Let us go and substitute. Let us go and substitute in for n. And let's put in n minus 1. So when we do this, and now I need to go and delete this stuff here. Y sub n simply becomes y sub n minus 1 equals y sub n minus 2 over natural logarithm of n factorial. We're decreasing, we're lowering the index of our units over here. And now we have z sub n minus 1 equals natural logarithm of n factorial divided by zn minus 2. Okay, now you might be wondering what the hell is the point of this trick that I'm doing over here. Well, I'm going to do a particular quick trick over here. I'm going to multiply these two sequences together right now. And when I multiply these two sequences together, y sub n minus 1 times z sub n minus 1, I am simply getting yn minus 2 over natural logarithm of n factorial. And then natural logarithm of n factorial to the top here, over z of n minus 2. And naturally, these natural logarithm of n factorials cancel out. So I end up getting y of n minus 2 over zn minus 2. But by definition, this is just x of n minus 2. So this becomes xn minus 2. So we're left with this incredible result that if we take the product of the numerator sequence, express this in words. If we take the product of the numerator sequence and multiply it by the denominator sequence at one stage, we end up getting the ratio for the sequence before that. That makes any sense when you do it beforehand. So yn minus 1 times zn minus 1 equals xn minus 2. And so when we reference here to this y sub n over z sub n, when we divide them together, this simply becomes nothing but x of n simply equals y sub n minus 1 times z sub n minus 1, which you would get again if you use the fraction property, over natural logarithm of n plus 1 factorial squared. Remember the flipping. And now we have this right over here. So this just becomes x of n equals xn minus 2 divided by natural logarithm of n plus 1 factorial squared. And we have solved our recurrence relation. We are done for step 2. Now, I don't know what this means when you have like a second C. It means that in order to show that the sequence is 2, we have two base cases. Meaning that if we were to go and solve this, or prove this particular statement, we would have to go and do so by the principle of strong induction. It's no longer weak induction. It's multiple cases, so it's strong induction. Okay, so now that we've proven that the recurrence relation in terms of ratios can be expressed as xn equals xn minus 2 over natural logarithm n plus 1 factorial squared, and we're given these particular two C's, it'll be purely easy just using this definition to go and derive all the other terms. I'm going to do it up to like 7 terms, so we're going to compute 4 more terms, x4, x5, x6, x7. Let's go and do it right now. So we have x4, that will equal to x2 over ln of 4 plus 1 factorial squared. And x2 is just this guy, so we just plug that in. And since this is squared, we can put all this together. So ln of 2, ln of 3 factorial. Ln of 4 plus 1 is 5, 5 factorial, this squared. And then this just stays in the fraction here, so we get ln of 2, ln of 3 factorial, ln of 5 factorial. All of this quantity like squared. We do x of 5. Now I do x of 3, because 5 minus 2 is 3. Now ln of 5 plus 1, that's ln of 6. And then, oh, pardon. So that's 1 ln of 4 factorial ln of 6 factorial squared. So this equals 1 over ln of 4 factorial ln of 6 factorial squared. X6. This becomes x4 over ln of 6 plus 1, 7 factorial squared. So I just get this result over here, ln of 2. Computation is tedious, is it not? ln of 3 factorial, ln of 5 factorial. Ln of, 7 factorial, all this squared. Starting to lose my mind right now. Ln of 2, ln of 3 factorial, ln of 5 factorial, ln of 7 factorial. All this squared. And finally, we have x7 equals x5 ln 8 factorial. And I'm not going to bother doing simplification. It's where you get the pattern idea. So this all just comes down to be 1 over ln of 4 factorial, ln of 6 factorial, ln of 8 factorial, and all of that squared. And that's it. Those are some values of the ratio terms of this sequence. Now we're going to go and then use these seeds now to go and construct the explicit formula to solve the emerald compound fraction. I will see you in the next part of the video now. Okay, and we're at the finale, ladies and gentlemen, because right now at this point, I have 7 iterations of these complex emerald fractions over here. And we're now going to derive the actual explicit formula. So I remind you here that x1 equals 1. That's very not interesting. x2 is natural logarithm of 2 over natural logarithm of 3 factorial raised to the squared. x3 is 1 over natural logarithm of 4 factorial, all raised to the square. x4 is ln of 2, ln of 3 factorial, divided by ln of 3 factorial, ln of 5 factorial, all raised to the square. x5 is 1 over ln of 4 factorial, ln of 6 factorial, all raised to the square. x6 is ln of 2 over ln of 3 factorial, ln of 5 factorial, ln of 7 factorial, all raised to the square. Then x7 is 1 over ln of 4 factorial, ln of 6 factorial, ln of 8 factorial, all to the square. Now from this, I hope that we can start finding some patterns that we can exploit in these particular entries in the sequence. And what do you notice? Well, I noticed one thing first off here, that each of these entries of these fractions have a square in them. So every emerald fraction is squared. I also noticed that if we're dealing with an even iteration, then each even emerald complex fraction has ln of 2 in the numerator, as we see right over here, etc., etc. And if it is odd, on the other hand, we end up just getting 1. So here, x3, x5, and x7. Finally, not finally, going on, as you increase n in each respective odd and even iteration, so if I go from x3 to x5 and etc., you notice how I have natural logarithm of factorials over in the denominator. Well, if I go from the odd one to the next consecutive odd integer, then the number of factors in the denominator keep increasing by a factor of 1. This is the same case for even iterations as well. From here, you have 2 factors, and now suddenly you have 3 factors here. And finally, for every even emerald fraction iteration, you end up getting odd numbers in the natural log factorials. The reverse is true for an even case. Even like, say, for example, x6, I am getting odd integers, ln of 3 factorial, ln of 5 factorial, ln of 7 factorial. And now, I hope that you can follow this. First, you need to remember that an odd number is defined as 2 times stuff plus 1, and an even number is 2 times stuff. And hopefully you remember your pi product notation, which is just a way to represent a series, not a series, a list of factors like being repeatedly multiplied together. With a dummy variable here and a dummy variable at the top respectively. Now, if we do this, I hope you will agree that we end up with this as our final results. X subscript of 2n plus 1 equals 1 over, and for my dummy variable, I'm going to use an alphabet consonant from my country, Thailand. So I'm going to use Wowan, Wowan, so Wowan just means ring. It's kind of like our version of like W. So I'm going to put Wowan equal 1, pi of Wowan equal n, natural logarithm of 2 Wowan. This whole thing should be a factorial, sorry, and all this squared. And if I do it for the even iteration, I should end up getting ln of 2, ln of 1, ln of n, of natural logarithm of 2 ln plus 1 factorial. And we are done! Yep, this is it. This is it. This is our explicit formula on how to compute any of these annoying emerald fractions. That's it. And the voice of love can't take me any higher than this. Oh, that was very cheesy, I admit. But I have to do that. So yeah, that's it. That's all the complex fractions for natural logarithms in general here. So I'm hoping that we can make this like a viral trend. So Papa Flamming has already derived this kind of like structure, and he has shown it for strings of ones being added together and the Gaussian, sorry, not the Gaussian integers, the triangular numbers, sequence of consecutive integers being added up together. Now, can you come up with this for a different kind of mathematical entry where we have something else special being written in the bars of our fractions? Let's go and sell these precious stones and make millions of them off the web. Am I kidding? It's just they're only the precious stones that mathematicians can afford. Oh well. So that's it. This is the end result. Hope you followed everything and hope you really enjoyed the video. Please feel free to comment. Again, as I mentioned before, like or subscribe doesn't really matter to me, but I'd like to like create a dialogue and potentially like create more of these videos. And if you have not already, please go and subscribe to Flammable Maths, please, because I just think that this idea of his was really brilliant and just a very great exercise in general. Okay, so until then, I hope to see you next time, ladies and gentlemen. Okay, ciao. I noticed when I was doing the last recording, a little bit of errors. I'm going to quickly correct that. The even and odd iterations of your emerald fraction diamond with logarithm is going to have 2ln plus 1, except like because we already have the pi product notation, we don't have to care about the factorial. So I omitted that in there. That's the correction I made here. And just in case, I wrote this in double factorial notation as well over on the right-hand side, which just means you take the factorials of even and odd integers depending on parity. So you can see about that if you're confused with that on Papa Flammy's channel, or you just look it up on Wikipedia. Okay, so again, please comment. And I guess a share wouldn't hurt as well. Hopefully get him to like even like notice this, be great. Okay, until then, see you guys in the next one.